Okay, let's start. Today, we will conclude chapter 4 and then go into chapter 5. We are now in week number 5. So previously, we stopped at example number 3, where we analyze the interstitial void or the space that can fill in by our alien atom, right? And you start to know that what mean by the coordinate number, right? What mean by coordinate number? So later we will use this coordinate number to identify the type of the defect that we have. Right? Okay, now today our focus will be on defect. We look at what's wrong with the material, right? So in general case, when we look at the material, we see crack, we see holes, right? So we start from molecule level first. Then we start about the big size, the grain breakout and all that. Okay. Now we know that we are now studying about metals. So metals consist of crystal structure. So we have covered 3 main types of crystal structure. We cover BCC, FCC, HCP. Then when we talk about imperfection or defect, so we can classify according to their geometry and shape. So when we talk about material, there are many ways of categorizing ideas or items that we want. But in this case, for imperfection or defect, we focus on their geometry and shape. First, we look at point defect later, which is in the material itself. In the material, let's say we have a pure material. I draw something on the whiteboard. So when we talk about point defect, it means that we focus on individual sphere or individual atoms. All right, something wrong with this size. It's called 0 dimension or point defect. But normally in my module, I like to use point defect. In some textbook, they use 0 dimension for point defect. Second one is 1-dimensional or line defect. What I mean by line defect? Line defect is that, or dislocation. Line defect, you know that what I mean by line? Line consists of many dots, right? Then it becomes line, right? So it's an upgrade of your point defect. So it means inside here, if we talk about line defect, it means that something wrong with more than one atom, but in the line form. It can be diagonal, it can be straight line, and so on. So in this case, I just give you a very simple one. So maybe it happened like that, right? I draw something on the whiteboard here. Okay. Now, then you upgrade from point, line, and then the third one, 2-dimensional defect. 2-dimensional defect means a higher level of defect. Normally, when it comes to 2-dimensional, 2D defect is the thing that you can see with your naked eyes. Okay, so this external surface, boundary layer, twins, we'll look at this later. Okay, and the larger one, once you develop more than 2D, it becomes 3-dimensional defect. Means that you will see that in a microscopic level. Okay, right. So if you take corrosion module will be more on microscopic, more on 3-dimensional effect, right? So for engineering material, we will look up to 2-dimensional defect. Okay. So yeah, we focus on these 3 types: point defect, line defect, and dimensional defect. So this is also one of the popular area when we like to ask you questions, because this section you can draw you can explain about that particular defect. Right. We look at first one, huh? So point defect again is a single atom is missing in the atomic site. Right. The keyword here, you can use whole, but whole sometimes is too general, right? Whole, it can be many atoms is missing, so it no longer fit into point defect. So we will recommend you to start to use vacancy. Vacancy, it refers to missing of one atom in the atomic site. Yeah, so first technical word for today is called vacancy. Vacancy actually is a missing of atoms, one atom. Huh? So as you can see on the screen here. Okay, so how does this single atom is missing is when previously we talked about solidification. So when you cool down the material, so the nucleus was formed, and then when they line up according to their orientation, sometimes the solidification happen too fast at that particular point, then they not enough to line up. So if you're in uniform body, you know, in the morning call, you want to line up. So some people they come late, and then there's a missing spot there. It's like you barbaris lah, right? So this one is how vacancy is formed. The rest you read, huh? Yeah. So this one is just a add-on information for you. How frequent that this vacancy happen in metals is about 1 in the 1,000 atoms. But this one, if you time up to millions, then you'll see some hole there lah. Okay. Then recall back when you deal with material, we deal with energy. Energy of formation is about 1 eV in the metals. So one vacancy is about 1 eV lah. What means one atom missing is about 1 eV. About lah. Huh? Okay. The rest you read. Huh? So how does this additional whole space here is missing? It can be plastic deformation. So you previously you learned about the pooling of material. So when you pull, if you draw tensile graph, you learn about tensile graph already, right? Yes, no? Not yet. Not yet. Okay. So we haven't learned. Later we will re-emphasize what is this one. So let's say you have a metals rock. You have a dot bond sample. Draw something on the whiteboard here. Huh? Okay, so this is a metal. So when you pull this sample, this is called tensile test. Tensile means you pull at the both sides, pulling up. Compress means the force is going in along the axis. So this is called tensile force or tensile loading. So when you pull metals and then you let go, it can go back. It's called elastic behavior. Yeah, you pull, you let go, it can go back to original shape. It's called elastic behavior. When you pull and then you let go, it stay there. It's like a bubble gum. You pull, it cannot go back, or it can go back a little bit, but it cannot go back to original size. That phase is called plastic behavior. So you pull, you let go, it go back to original size. That is fall between elastic behavior. Normally, if you do test stress strain graph, later we learn about this graph. So you go up means in the line, in the straight line means you let go and then you pull and let go, it become to the original size. Once it pass the elastic limit, we will go to plastic behavior. Means you pull, you still can go back, but a little bit, but not back to the original size. It's like a bubble gum, right? Then after you pull plastic already, then it break. Break. Okay. This one is break. In material, we don't use the word break, we use fracture. Fracture. Okay. So later we look at this graph later. It may be in chapter 5 or chapter 6. Rapid cooling. And this one is bombardment of energy particles as the neutron means you give energy. Give energy like X-ray. Or you do sand sandblasting. Do sandblasting for polishing the surface. So sometimes the silicon will hit the pure metal atom and then the pure atom will peel off. Okay. So this is the first one, vacancy. What is vacancy? How vacancy form? Okay. The idea of vacancy is single atom, and then how it form? It always based on rearrangement of the atom. The keyword is arrangement of the atoms. So how does this form? Is because the atom was not enough time to go to the position. Okay. Yeah, due to cooling, solidification, and so on. Okay. Let's read. This first equation for today is called equivalent number of vacancy. Means you find the numbers of space or missing atom in the point defect category. Given you and V means vacancy, and exponential means E power something minus QV AT is a constant value. So again, one more constant value you need to memorize, which is the K Boltzmann constant, 1.38, 10 power negative 23. The unit is Joule over atom Kelvin. When you see Kelvin, means the temperature you use here will be Kelvin. Okay, because the Boltzmann constant, you are using Kelvin unit in the calculation. So remember to change the temperature into Kelvin by plus 273. Okay, so QV is the energy required for the formation of vacancy. Just now, you was introduced to one number, which is 1 eV. But different material have different energy to form the vacancy. This one normally will be given in the question. Okay, this one normally will be given. K value won't be given. Expect you to memorize. And this one is exponential, E power something. Okay, let's apply the formula. So calculate the equivalent number of vacancy. So actually it's quite direct. So when you see the equivalent number of vacancy, it means you calculate the capital N sub V per meter cube per meter cube for copper at 1000 Celsius. All right. Now energy for vacancy formation is given 0.9 eV per atom. The atomic weight also given, of course, when it comes to test or final exam. Atomic weight won't be given because you're given periodic table. So you have to make fully use of the periodic table. Yeah, remember atomic weight normally won't be given. Density is given 8.4 respectively. So you go back to the equation just now. EV equal to N. N is what? Total number of atomic site. Okay. Okay, you have Boltzmann constant. You have the R. Yeah, this is information. This is cost constant R, 8.31 Joule mole per Kelvin. Still using Kelvin. And okay, so we apply the thing. So we need to find the number of n. So number of n given by Na rho over the atomic weight of the copper. So you plug in the number. Na is Avogadro number, 6 point something, 10 power 23 per mole. Then rho is the density. Density is given. But remember to change into unit SI. You change cm cube into meter cube. This is a conversion. Then the atomic weight, this one normally from periodic table, but this question give you for your convenience. So 63.5. This one. It's a conversion for your cm to meter. Understand? Means you change cm cube to meter cube. So what is cm cube? 10 power negative 2 meter cube. So you change cm to meter lah. 1 cm equal to negative 2 meter, right? So you convert lah. This one actually is 10 power negative 2 meter over power 3. So this one equal to 10 negative 6 meter cube. It's just a conversion for your meter cube to meter cube. Okay, so if you look at this question, we expect you know this calculation of n in the equation. We did this one. Number of atomic type per cubic meter of copper. We calculate the n here. N equal Na rho ACU. Okay, so this is the density. If we re-engineer the question, you should be able to find the density. If we give you the mass of 1 kilo, and then what is the size of that material, you should be able to find the density. In this case, all information is given for your convenience. When we come to assessment, we are testing whether you know how to calculate density. Yeah. Then you press the calculator, you get your n equal to 8 something atom over meter cube. We are using meter cube. Once you find your n, you plug in the numbers. All right, you plug in the numbers, you use NV equal to n exponential minus QV divided by KT. You plug in all the numbers. All right. Remember to change the temperature into Kelvin. You're given in 1000 Celsius, so 1000 equal to 12373 Kelvin. All right, the rest is calculation. All right. I'll try to understand the working, try to understand the logic behind the equation, right? Because the numbers will change in the test or final exam. Okay. There is an equation to calculate Boltzmann constant as we go deeper, but in this case, just use this standard value for Boltzmann constant. As you can see here, there are two value for your K on the screen here. One is 1.38 10 power 23. The unit is Joule over atom Kelvin. Another one is in EV term, 8.6 10 power negative 5 EV over atoms. So you need to read carefully what is the unit given in the question. In this case, the Boltzmann constant was given in a EV term. Right, the formation is given in EV term. If the energy is given in a joule, you have to use this one. You have to use 1.3 joule over atom Kelvin. Be careful on the statement that you see in the question. So one is temperature, must be in Kelvin. Second one, your Boltzmann constant, you have two value depending on the question. If the question gives you the energy formation in joule, then you use 1.38 joule over something. If the question is like this one, example 4, you are given in energy formation in EV, then you use the second one, 8.62. Yeah, you have two value of Boltzmann constant, depending on the question. Careful, this one. Next one, point defect. Just now is the missing space, missing atom, right? This one is missing atom. Point defect also can be defined as additional atoms or alien atom in the atomic site. It can be a space, a small space, or it can be alien atom or not the same material as the site of the around the members. It can be two, it can be space or it can be additional atom. This one. Okay. So they have two. Now we'll look at what happens if you have a interstitial defect, which is like what you see on the screen here. There is a dark blue color atom, which is a bit different from the surrounding atoms. This type of defect also called point defect. This one is important when we learn about ceramic later. We learn about alloying, metal alloying. This is very important. So there are two types of point defect as you see on the screen here. So if you are being asked to explain about point defect, this diagram is what we expected. You draw vacancy, you draw self-interstitial, you draw these two, and then you explain what is point vacancy. Or even you draw this one, you explain a little bit. Either one missing atom or there's an additional atoms in the atomic site. Okay, the keyword is missing atom or additional atom in the atomic site. Then you draw this diagram. Okay. This one is a very direct explanation that you see on the screen here. Very direct. Okay. What happened to ionic crystal? Ionic crystal, they are more complex because they are sharing their electron, right? So there is something called Stocky imperfection, which is normally happen in the ionic crystal. So you can see there are two types of imperfection here on the screen here. One is called Stocky, one is called Frankel. Same, one is space, one is additional atom. It's like the two type of imperfection that we see just now. Huh? So this one is the definition for these two types. Okay, you read on the slide, sir. Okay, again, things that you can draw, things that you can explain, it will be part A of the question. So example, something like this. You can draw, you can explain, that one is part A question. Part A, B, C. Okay. Okay, this one also you read. Next one, we go into line defect or dislocation, or this dislocation. Just now we already done for vacancy. Now we go into dislocation, or line defect, line imperfection. So let me give you the diagram. Oh, okay. So how does this line defect or dislocation happen? Again, solidification, permanent or plastic deformation, still the same like your vacancy just now, same. Vacancy, condensation, and atomic mismatch. So this one is special for line defect. There are two types of dislocation. We call it H and screw type. I will show you the diagram. You have two types. So point defect, you have two types. Line defect also you have two types. Okay, point defect you have two types just now. Line defect you have two types called H and screw. What I mean by this one? Then you combine two, it become mixed. Okay, you combine these two. If the object have these two, then it become mixed dislocation. So I'll show you the first one. It's called H dislocation. What I mean by H? There is a missing atoms at this site. So this one is like 1, 2, 3, 4, 5, 6. The one that I pointed at the center of the screen here. You have six row of atom here. But when you come to the next row, one atom is missing. So the neighbor will, you only have 1, 2, 3, 4, 5. So there is a missing a row of atom here. Okay, it's a row of atom was missing. So this one is called H dislocation. And you're given a symbol, inverted T. What I mean by inverted T? It means it stopped at this location. Means the complete crystal structure or complete atom site is stopped at here. The rest will be less lack of row of atoms. Okay. So it can be inverted T or T shape. It depends on the arrangement of atoms. This one is inverted T. So when you draw T, it means the top here is missing, right? So we just reverse the diagram. Okay. Again, in line defect or dislocation is a row of atom is missing. It's a row of atom is missing. So it fall under dislocation. The one that you see here is H dislocation. So if you combine, this one is in three-dimensional. So if you draw the complete atomic site, so you can see the line 1, 2, 3, 4, 5, but here you only have 1, 2, 3, 4 here. So one is missing, line is missing here. So you just draw a inverted T at this location. Means there's a defect over here. Then you use your there is a vector. There's a vector for B. This is called slip of a Berger vector. Berger vector. For line defect. And this one was perpendicular to the dislocation line. What does this perpendicular? If you look at this diagram, you see this is the one that is missing, right? You see this one? You see this one, right? So you see this is the missing line, right? So this Berger vector is 90° to the dislocation line. Yeah. It's important to know the direction. Huh? Okay. Berger vector only deal with edge dislocation. Huh? There are two types of line defect. Edge and screw. B, the Berger vector is deal with edge dislocation. This type of dislocation, they are non-equilibrium defect. Means non-equilibrium means the force is not same around the atom site, and they store energy in the distorted region of the lattice around the dislocation. So if there is a missing atom, right? So there will be a tension and compression site. Right? There will be a tension and compression site. How do you know which one is which one? Huh? I draw something on the whiteboard. Let's say I draw the atomic site. Okay, so all these are row of atoms. Huh? They are row of atoms. They are row of atoms. When line defect happen, what happened? Let's say this one gone, this one gone, means the whole row is gone. So you don't have atom here. Then you drop in one symbol to represent edge defect, inverted T here. Okay, so when you have missing members here below, right? What happened to this one? They will always try to form together. So this one will squeeze inside. Correct. These two will try to go inside because there's a space there. So you know that material we always try to handle loading on it, right? So when there's a loading, this is a space. So the outside external force will try to squeeze these two. When try to squeeze these two, what happened to this one? So it will go inside. There's a force. If you look at this row, just now we tell you what is tensile, right? Tensile is there's a force pulling at both ends, right? So this one will go in. So this one also will pull. So this form a tensile test. And then here, because it's pull in, these two pull in, so it will form a compression on this region. It's try to squeeze in, right? So this one will cannot squeeze. So this one will form compression. This one is tensile. So you have compress and tensile. All right, tensile, compress. Any question? Make sense to you? Okay. Okay. So again, how do you input the notation in your diagram? First, if you see H dislocation, it means some row of atoms is missing. And the Berger vector is always 90 degree to this line. Berger vector always 90 degree to the line here. Okay, so if you draw inverted T, normally vector will be in this direction. Huh? This is your Berger vector, B. This is your H dislocation, or inverted T. Okay. Now we look at screw. So let's say you have a material here, and you cut the material in the highlighted region here, like what you see here. When you cut this one, your atom will try to move up and down because there's a free movement between the layer here, right? So there is like an earthquake. It will slip like that. The slip up or down lah, never mind. Huh? But the motion will be slipping like that. So when it slip, you will form a screw dislocation. So in this case, you see the direction of the screw. So this is you go to the edge of the plane here, like what you see on the screen here. The plane here, there is a stopping point there. That stopping point become the screw line dislocation. The screw dislocation line means you draw a line on the stopping plane there. Okay. Then how you draw the Berger vector for screw? You use your right hand rules. Left, right hand rules. So this one go up. So curving of your four fingers will give you direction of your Bergers. Okay. Yeah. So the catching part is the slice, the cutting plane, and then you look at the screen here. Berger is pointing down. It will tell you the sliding plane. Huh? Okay. The rest you read. This one is important when you want to cut metal because normally you cut with the machine, and the effect is always happen because of the shear loading. You cut metal using shear force. Even you cut paper also same, right? Okay, the rest you read. When you talk about screw defect, one keyword is shear for line defect screw dislocation. Is the shear force. Shear, you know what is shear, right? You know what is shear force? How you calculate shear force? Okay, I'll draw something on the whiteboard. Huh? Let's say you have an object. You know that when you have a force acting perpendicular to the area, this force, this is area. So when the force is 90 degree to the area, what do you get? You get stress. Stress equal to force divided by area. Have you learned this one? Yes, right? No. Have you learned this one? No. Physics, statics, dynamics. Huh? Yes, correct. So it's pressure, or we call it in material or in engineering, we call it loading, or we call it force, or we call it, it depends on what you define, right? So the force is perpendicular to the area. We take how you calculate the stress, force divided by area, but must be 90 degree. If we have two force pointing out, it become tensile loading or tensile stress. Make sense? Now, Another case, same object, the area. Now what is different? Now the force is parallel to the surface. Same. The force is parallel. It must be coupled to balance the force and moment, as you learn in statics. How you calculate stress? This is called shear stress. Same, you take force divided by area. But you are taking the force that is go parallel to the area. This definition is called shear stress. So it depends on the direction, or we call it vector of your force. Okay. So you need to be careful. Sometimes tensile, sometimes shear. Don't be confused with, don't assume that all the force 90-degree or shear loading is the same. They are not same. Tensile loading always 90-degree. Shear loading always parallel to the area. So what happened if you are given an object and the force is working at a certain degree theta force? Then this diagram will give you two kinds of loading, tensile and shear loading, or tensile stress and shear stress, because you can split into two components, right? Make sense? This one you can break into two components, force shear and force tensile. It's a vector, right? Vector you can split. You can split, right? Of course, this one I assume is a 2D. 3D one you can have another magnitude lah. You have a X, Y, Z axis. This one I assume happen on the plane. Okay, so we go back to dislocation. So this one, when the force is parallel to the surface here, it becomes shear. That is not tensile. Okay, and this is the focus point where you can cut material. We call it the energy focus point. So this one will work. What happens if you try to pull this one? Where's the direction of dislocation? Going this way, right? When you pull up and down, this dislocation here, where will it go? It go to this direction, right? So how do you tell the audience or tell your readers that when you what is the relationship between the direction of the dislocation and the applying force? Will be perpendicular to each other. Make sense? So you pull. So this hole here, or this dislocation here, will work perpendicular to your force. Okay. So again, Berkel vector for screw is parallel to the dislocation line. It's parallel to the dislocation line. Just now, H vector, H dislocation is 90-degree to your H symbol or H side. But Berkel vector is parallel when it comes to screw dislocation. Okay. So how do we ask you your how we test your understanding between H and screw? Sometimes we give you a statement, how the atom move when in the process, when you process material. Then we'll ask you predict the type of dislocation happen. Okay. So this is another information for you. So in this case, you will have H. This one is the screw dislocation, right? So H dislocation. So you push this one in, so you will anti-clockwise direction. One is from the top, one is the three-dimensional diagram. Okay. So this is called Berger vector. That just now the statement, the Berger vector is parallel to the dislocation line. Okay, this is what mean by the parallel dislocation. Okay, so again you can see Berger vector actually is the distance traveled by the defect side. It's like earthquake, how far the earthquake happened. Okay. So we have two, then there's a mix. If you have a mix, then it mix two lah. Okay. So like what you see on the screen here, you have a mix of H and screw. So this is H. This is H. So you see the line is missing. So this one is H. How you draw the symbol for this H? Inverted T over here. Huh? Then this is a screw. When there's an earthquake, go inside the inside the screen here. So this is a screw, and Berger vector is parallel to your screw axis. It must be parallel. Huh? This one is perpendicular. Okay. So this is how you identify lah. How you identify. Okay. So this one is okay. The rest you read. This is another three-dimensional for you. So you have mixed dislocation. On the left-hand side is the screw. Right-hand side is the H dislocation. Okay. So this on the B here, diagram on the left or right here, is from the top. So it's being pushed in to the top. It becomes screw, and one missing line happen in the top of the diagram. Okay. Observe what is happened to the Berger vector here. Okay, this is the under microscope. You might be seeing this one in your lab, and you need to explain about this one. Right. Okay, we have a break. Later go into planar defect. Huh? Okay, 10 minutes. 10 minutes break.